Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. We're talking about ether. I want to compare some physical properties of ethers with alcohol and water, and then later we will switch to how to prepare ether molecules. First thing is going to be the bond angle. If you look to water, it has two hydrogen atoms versus, for example, alcohol. Alcohol, it has just one hydrogen. Well, when we turn to ether, we lost both hydrogens and we replaced them by two bulky groups. And so as we increase those bulky groups, the bond angle is going to get bigger because we will have more steric effect, or technically we will have a repulsion between them. So I'm going to say the steric effect, it will be subject to the size of the particles, and we have CH3 that is bigger than hydrogen. The more methyl groups we have, the higher repulsion we will have, or steric effect between them we will have. So I expect the bond angle to be higher. And as you see, that's true. Next one is the boiling temperature. Boiling temperature of alcohol is higher than boiling temperature of ether. Okay. And what's the reason behind it? Reason behind it, alcohol is capable of donating H plus or accepting H plus. This is alcohol, number one, is accepting H plus, okay, accepting H plus. And the second one also is alcohol. Okay, they are identical in alcohol, and it's donating H. So number one is accepting, and if I call this one number one prime, and it will be donating H plus. And remember this, because we have acidic H on both of them, that acidic H can get involved in hydrogen bonding. So technically, ether and the alcohol molecules do have hydrogen bonding between them, okay, which we don't have it when it comes to pure ether. There is no acidic H, so there will be no hydrogen bonding between two ether molecules. Okay, here we have an ether, so I'm gonna call that one ether, and second one is alcohol. And alcohol is capable of donating H plus, and ether is capable of accepting. So ether can accept H, but is not capable of donating H plus. And that means ethers alone are not going to have hydrogen bonding, and because they don't have hydrogen bonding, they will be left with dipole-dipole and dispersion forces. Their boiling temperature will be less than alcohol. And now let's talk about, again, about the boiling temperatures that we have here. Why the boiling temperature is changing dramatically. The reason behind it, and for alcohol, the strongest force, it will be hydrogen bonding. Okay, so for the first one, strongest force, it will be hydrogen bonding. For this one, the second molecule, and the strongest force, it will be dipole. Well, for alkane, the strongest force, it will be dispersion. And remember, we do have dispersion and dipole for methanol or ethanol as well. So I can say I have dipole, and 3 dispersion as well. Okay. For ether, we have dipole as the strongest, and then dispersion. Okay. But I wanted to highlight the strongest one. Strongest one for alcohol is hydrogen bonding. For ether is dipole, and for alkane is just dispersion. And that's the reason that we have such a huge gap between boiling temperatures. As we increase, as we increase the size of the particles, the boiling temperature will go up. Why? Because the dispersion force, or the intermolecular forces, okay, is subject to molar mass. And as we increase the size of the particle, and the molar mass, it will go up, so dispersion force will go up. And we started with methyl, we replace it by ethyl, and next we replace them by propyl. The more carbon we have, the higher dispersion force we will get. So that molecule is going to have higher boiling temperature, simply just because of the size of particle or the molar mass. Now that we reviewed some physical properties, we're going to switch to how to prepare those molecules. And the common method is the Williamson method. And we use the Williamson methods. Technically, first reaction is going to be acid-base reaction, and the second one it will be SN2 reaction. So the second one it will be SN2, and the top one it will be acid-base reaction. Okay, you need to be careful when it comes to SN2 reaction. SN2 reaction, if I write here the rate for SN2 reaction, we said methyl. Okay, if we have the halide attached to methyl, reaction it will be faster than a primary carbon, then a secondary, and that one faster than a tertiary. In fact, the tertiary will not go through SN2 reactions, and it will go through a different mechanism. We are not going to get SN2 for tertiary halide. Okay, so whenever you design such a like a reaction, you have to pick halide, the alkyl halide with the least steric effect. So put the halide on a carbon with the minimum steric effect. Okay? If you switch it, in that case, you will have elimination reaction instead of forming ether. And let me show you those two possibilities. So first step, we'll have sodium halide. We know sodium is going to generate halide, and forgive me, sodium hydride. Sodium hydride. And the hydride, it's going to be a strong base, and it can react with any alcohol. And so first step of this reaction is going to be just simply reaction of acid and base, and the alcohol it will behave as a base. It will as an acid. It will technically give H to the hydride, and the hydride with a negative charge it will take that H, and so we get -1 here for the alkoxy plus half a mole of hydrogen gas. Okay, now what will happen to this species? This is a strong base / strong nucleophile. Okay. Now, this one is going to react with the alkyl halide because it has a negative charge. It will react with the carbon. Okay. So we will have a carbon that it has 3 hydrogen atoms, and also there is an iodide attached to it. So this oxygen it will go after carbon, and it will technically attack that carbon. So we will have addition. And that halide, it will take those 2 electrons and it will leave the system as iodide. So we get ether. On one side, we will have tertiary butyl. And other side, we will have CH3 and plus I minus. Okay, what's the name for this one? It will be tertiary butyl. And then we say methyl ether. Okay, and of course we got iodide. Now, what will happen if I switch their position? Okay, I said that we might get elimination because the higher the steric effect we will have, the less chance to get SN2 reaction or SN2 products. Okay, so first step of this reaction, the H minus is going to react with the alcohol. And we will get half a mole of hydrogen gas, plus we get the methoxy. CH3. Oh, this one it has a negative charge. Okay, this is a strong base / strong nucleophile. Okay, nothing surprising until now. Now, what will happen if I react this with the alkyl halide? Okay, our alkyl halide is bulky, but the base is not. So I have a base. It will reach carbon, and that carbon it has. It has a 3 methyls group and iodide. Okay, this is a tertiary carbon. Reaching a tertiary carbon is going to be harder for our nucleophile. So nucleophile cannot easily make it to that carbon. And instead of that carbon, and it will behave as a base. Okay, not a nucleophile, as a base. And this time, because we do have H atoms there, those H atoms are sitting on a primary carbon. Reaching those hydrogen atoms is way easier. So very soon, that's a methoxy group, it will go after the hydrogen atom, and it will take them out of the system. So we get this. We get methanol. Okay, and now those 2 electrons they will be given to carbon. We will get a double bond, and the iodide it will leave the system. So we get iodide again. And what else? We will have a carbon attached to another carbon, and we do have 2 hydrogen there. Now our central carbon still is attached to 2 more carbons. So we got the double bond. Okay, and those are CH3, CH3. Okay, so instead of getting ether, we got elimination product. The reaction went through E2 mechanism. And again, our nucleophile behaved as a base, and we got methanol instead of ether. So this reaction failed to give us ether. If I go back, I said whenever you design this reaction, put the halide put the halide on a carbon with the least steric effect. Okay, and then the second one, we put it on a carbon, on the tertiary carbon, and as you see, tertiary carbon does not prefer to go through SN2 reaction. In fact, we went through E2 reaction. Next, and the last mechanism, it will be the alkoxy mercuration, the demercuration. And we use this method to make an alcohol. The OAC stands for acetate, and sodium borohydride is a source of H- or hydride. And if we use alcohol instead of water, and this time our nucleophile will be the RO. It will be the nucleophile. So this piece, it will be the nucleophile. And we will get ether instead of alcohol. Okay, so first step of this mechanism is going to go through this way. So we will have a double bond. And next, mercury, it will attach to both of them. It will have a positive charge. And now we will have one OAC, one of the acetate left the system and turned to one OAC -1. And what's the reason behind it? The reason behind it, this, and the double bond behaved as a nucleophile and attacked actually mercury, and kicked out one of the acetate. Okay, so we got this intermediate. Next step, the ROH will get involved, and this piece, RO, it will behave as a nucleophile, and it will attack a carbon with more substituent. Which carbon? This one is the one on the left, is a tertiary carbon. Well, this one is a secondary carbon, so the attack will happen on a tertiary carbon. And if that one happened, we get this. We will have 3 R's attached to this carbon. And what else? Here we will have hydrogen R here. And now we will have the mercury attached to OAC there. Okay. And the next step, this one is going to react with the sodium borohydride. And the hydride with 2 electrons, it will attack this carbon, and it will kick the mercury out. So mercury, technically, it will take those 2 electrons and it will leave the system. And so what do I get at the end? I get this. I will have 3 carbons attached to the carbon on the left side, and this carbon, we will have R, and we got what? We got hydrogen here. Okay. And so now when I made a mistake, and the mistake I made, it was this, and this one's supposed to be ROH, my bad, RO. And so let me fix this one. I'm sorry about it. We got RO there and hydrogen. Okay, and remember, we had hydrogen from the beginning. There was hydrogen, so the blue one is the hydrogen that we had from the beginning. This one, and through this method, we put the hydrogen. Okay, we put the hydrogen and on a carbon with less technically substituent, and or the hydride was added to carbon with less substituent, and the RO added to carbon with more substituent. And on the left side, as you see, we have oxygen, technically bridged between that oxygen is bridged between 2 carbons. So we got alcohol. And I'm going to stop the reaction. Sorry, I'm going to stop the lecture here, and thank you very much.